Good morning, students. Our next theorem is Tychonoff product theorem, which states that product of compact topological spaces is compact. It means if we take a collection consisting of the members xi with topology to I, here I belongs to the index set. This is a collection of compact topological spaces, and X is the corresponding product topological space. Then we are to prove that X with the product topology tau, that is compact. Now, by definition, X, which is the product of xi's, this is the collection of all those elements X which are of the form product of xi, where xi belongs to the topological space xi for every I belonging to the index set. And let us take tau be the topology on this set X, which is defined as follows. Let us take alpha, which is the collection of all those subsets of X which are of the form of product of AI, where AI is equal to xi for all except one I, and for that one I, AI belongs to tau I. This type of products are called very special products, which we already discussed in product topological spaces. And such type of products, they forms defining subbase for the product topology. And beta, which is the collection of all the finite intersections of the members of alpha, they forms defining base for the product topology on the set X. Now, we are to prove that the topological space X tau is compact. In order to prove it is compact, we prove that every ultra filter on X that is convergent. So let us define the projection map, ith projection Pi from the product space into the ith coordinate space xi by taking an element x belonging to the set X, because X is the product of xi's. So by definition, the point X will be of the form product of xi, where xi belongs to the ith coordinate space xi for every I belonging to the index set. So we can define the ith projection by Pi of x is equal to ith coordinate of this x. Ith coordinate of this point x, that is xi. So we have defined Pi of x is equal to xi. Now to prove X is compact, let us take an ultra filter F on the set X. Now to prove X is compact, we are to prove that this ultra filter is convergent. Now let us define the image of the filter F under the ith projection Pi. By definition of image of filter, this is a collection of all those subsets B of X which contains the image of some member of filter F under Pi. It means B contains image of A under Pi. Here A is some member of filter F. Now, because image of an ultra filter is again ultra filter, and here because F is ultra filter, so its image under the mapping Pi, that is an ultra filter on the topological space Xi. Now, because each Xi is compact, therefore every ultra filter on Xi will be convergent. So Pi of F, that is convergent for every I belonging to the index set. Now by definition of convergence of filters, there will exist a point xi belonging to the topological space xi such that pi of f converges to xi. And this is true for every I belonging to the index set. Let us take X is the product of these xi's. So by definition of product topological space, this X belongs to the set X. Now it remains to prove that filter F converges to the point X. In order to prove filter F converges to point X, we prove that neighborhood system of this point is contained in filter F. So let us take an arbitrary member W belonging to the neighborhood system of point X. It means W is neighborhood of point X. So by definition of neighborhood, there will exist a member G from the topology tau such that X belongs to G is contained in W. Now G is a member of topology tau and beta is base for this topology. So by definition of base, there will exist a member from base. That member we have taken as B such that X belongs to B is contained in G. Now because B belongs to the defining base for the topology, and by definition of defining base, this is the collection of finite intersections of members of subbase, and therefore there will exist finite number of members h1, h2, h3 up to hn from the subbase such that B is the intersection. It means B can be written as intersection of hj where j varies from 1 to n. Now because X belongs to B, it means X belongs to this intersection, and therefore by definition of intersection, X belongs to every hj where j varies from 1 to n. So image of X under Pi will belong to image of hj under Pi. Also this set is open in the topological space Xi. Therefore by definition that will be neighborhood of Pi of X. Pi of X is Xi. It means Pi of Hj is neighborhood of Xi. Now this filter Pi of F, this converges to Xi. So by definition of convergence of filters, its neighborhood system will be contained in this filter. Now because Pi of Hj, that is a member of neighborhood system of Xi, so that will belong to the filter Pi of F. Now because this belongs to the image of filter F under Pi, so by definition of image of filter, this will contain image of some member of filter F. Now taking Pi inverse on both sides, we get Hj is contained in Gj. Now Gj, that is a member of filter F, and we know that if a member belongs to a filter, then its superset also belongs to the filter. Hj being the superset of Gj, that will belong to filter F, and this is true for every j varying from 1 to n, and therefore the intersection will also belong to the filter F because a filter is closed under finite intersections. So intersection of Hj where j varies from 1 to n, that belongs to the filter F. This is B. It means B belongs to the filter F, and therefore from the second equation, G also belongs to the filter F being the superset of B. Now because W is the superset of G, and therefore W also belongs to the filter F. So we have proved W belonging to the neighborhood system of point X belongs to the filter F. So we can say that neighborhood system of point X is contained in filter F. So by definition, this proves that filter F converges to point X. So we have proved that every ultrafilter on X is convergent, and therefore we can say that X is compact. So this proves that product of compact topological spaces is again compact. Now, in the next theorem, we'll discuss the normality of compact regular topological space. So let us take a topological space X top, which is compact and regular. We have to prove that this topological space is normal. Now, in order to prove X is normal, we have to prove that disjoint closed subsets of X have disjoint neighborhoods. So let us take A and B are disjoint closed subsets of X. We have to find their disjoint neighborhoods. Now let us take X belongs to the set A. Now because A and B are disjoint, so X will not belong to B. Now B is closed subset of X and X does not belong to B. The set X is regular, so by regularity of X, there will exist disjoint neighborhoods of point X and the set B. So we can say there exists a neighborhood Gx of the point X and neighborhood Hx of the set B such that their intersection, that is phi. Now, because X belongs to A implies that X belongs to Gx. So we can say that A is contained in union of Gx for X belonging to A. So if we take a collection E consisting of all these members Gx for which X belongs to A, then this collection is open cover for the set A. Now, because A is closed subset of compact topological space, so A is compact and therefore every open cover for A will have finite subcover, and E being the open cover for set A will have finite subcover. It means there exist finite number of members Gx1, Gx2, Gx3 up to Gxn from the cover E such that A is contained in their union. Now let us denote this set by the set G. So from here we have obtained A is contained in G and also G is open. So we can say that G is neighborhood of A. Now it remains to find the neighborhood of B. So let us take the corresponding Hxi's and let us take H is their intersection. Then H being the intersection of finite number of open sets, H is open and also B is contained in H. So we can say that H is the neighborhood of B. So we have obtained neighborhoods of A and B. Now it remains to show that these neighborhoods are disjoint. G is neighborhood of A, H is neighborhood of B. We have to show that G intersection H is phi. Now, because the intersection of Gxi with Hxi, that is phi for every I varying from 1 to n, and H is the intersection of these Hxi's. So H is contained in Hxi for every I varying from 1 to n. So we can say that intersection of H with each Gxi, that will also be empty, and therefore the union of these members, that will also be phi, and therefore we can say that H intersection G, that is phi. So we have proved that disjoint closed subsets of X have disjoint neighborhoods, and this is the definition of normal topological space. So this proves that the topological space X2 is normal, and this completes the proof of the theorem.